So let's do that. So sine theta is mb divided by ma. At this point, if you got your masses backwards, or if the problem were set up wrong so that mb is bigger than ma, this is the point where it would come out. Because sine of theta cannot be bigger than 1. mb has to be less than ma. So this is 0.25.
So at that point where sine theta equals mb over ma, if it equals over 1, do we just switch them because we might have gotten them backwards, or should we go back?
I would recommend going back to see if there's some other mistake. It might be as simple as flipping them. However, from a grading point of view, if I see ma over mb and then suddenly you flipped it for no apparent reason, just because so the math would work out, I then start looking for all the little things. Because it also might be, you get something bigger than 1 and you're saying the problem's not possible.
So it's 0.25, that's right. I mean, it's,
If it's right.
no, it's 0.25, it's right.
Okay.
I agree.
Okay.
You said sine, so what are we trying to find?
So theta is,
0.25.
so that's sine of theta.
That's sine of theta.
Yes, so theta is
I got 14.48 degrees.
14.48
Yes.
degrees.
Yes.
All right.
Huh?
Sine of theta is 0.25, so theta would be the arc sine of
Oh.
0.25.
I was like, wait, what? Okay.
And in this particular case, you might get away with, if you're dealing in radians, with 0.25, but, all right, so we end up with MA, which is 0.2 times 9.8 times 0.7 times the cosine squared of 14.48 degrees divided by 0.05. That's v squared. All right, so let's see. That's probably 8. I'm thinking v squared is somewhere around 25.
At 25.72.
All right, and so v equals
5.07.
finish it off.
Meters per second.
Meters per second.
All right.
Is v squared the 25.72?
Yes. Yeah, but this is v squared. Questions before we solve this a different way?
I had another question about the sine theta equals mb over ma.
Good.
How would we get that wrong? Could it be cosine theta?
A couple of places where this sometimes mess up. If we'd assigned this as theta, then that would have been, then we would have had ft sine theta and ft cosine theta, so that would have gotten the sine and cosine backwards, which wouldn't have got you a bad answer. If MA is less than MB, then typically A wants to fall, but swinging B keeps A from falling. If MA is less than MB, then A is not gonna fall. The B would slide down and A would go up, so that it's impossible to, swinging B would only make A go up faster.
So the main problem would be if you did your decomposition wrong?
If you did the decomposition wrong or broke something down wrong. Or if I set up the problem just to see how many people recognize that, oh, this can't be done. Or I set up the problem wrong by accident because I made a careless error when I was doing the problem. All right.
That was a yawn, Joey.
Let's solve it slightly differently. So we have a speed of 5.07 meters per second. How long does it take for the mass B to go around in the circle?
We don't know that.
How would you find it?
Could be the circumference of the circle.
Keep going.
And you take how many meters that would be, and then you use your speed.
Okay. So speed is distance over time. The distance is indeed the circumference of the circle. Now we know what theta is. So this is 2 pi times L cosine theta over T is equal to 5.07. So my period, the time it takes to go around once, would be 2 pi L cosine theta over 5.07, which is 2 pi times 0.7 times the cosine of 14.48 degrees divided by 5.07.
It's just, is it 07 or just 0.7?
That's L.
I know, because you were saying 07.
Oh, it's 5.07 and then 0.7 for L.
Okay, never mind.
I'm not fast misspeaking. All right, so what does this end up being?
So,
I think you're right.
0.84.
0.84 seconds. All right.
So all we did was just plug in R, which we found with L cosine,
Yes.
and then just change the equation around so we can find T.
Yes. That's it.
so would we get,
This isn't the shocking revelation, the different way of solving. I'm just piecing us into something else.
so would we be given a problem that we have to solve for velocity and then use velocity to get our, never mind.
Okay. We would use it to solve for speed, not velocity, but well, let's explore that a little bit more. All right, so we know how much time it takes to go all the way around. So if we think about it in terms of angular speed, regular speed is distance over time, angular speed is angle over time. So if it goes around the circle once, what is the angle?
360.
Units become important here.
360 degrees.
Okay, and how many radians is that?
2.
I've heard various things, but I heard everything said needed to be 2 pi over the period, which is 2 pi over 0.84. And so what do we get as the angular speed?
.47.
7.479 units.
Oh, wait, hold on. Yeah, it's the same,
Meters per second.
angles per second.
Radians per second?
There we go. As a group, we figured it out. It would be 7.479 radians per second. So angular speed is just dealing with how fast is it rotating and not how fast it's actually moving. That was awkwardly worded, and hopefully you caught the spirit of what I was saying.
Okay, so it's trying, so what does that mean, 7.47 radians per second, so in
So radian is about that's 1 radian. And so it takes, does more than 7 of those in a second.
Okay. But it doesn't tell us how fast it's going, it's just how many it clears, just 1 second.
If you cut the string, it's not telling us what that linear speed is, no. All right, let's take a look at this from a different point of view. We had ft cosine theta equals mv squared over L, oh, sorry, not the way I wanted to go, equals mv squared over r. This is one of the equations we had before. But if you recall, at the end of last class, I talked about the fact that centripetal acceleration, v squared over r, or omega squared r. There is an alternate form. So if I went with omega squared r, I get ft cosine theta is equal to m omega squared r. If I do that, then, and I guess that was mb. When I make my substitution for r, which is L cosine theta, I have tension is equal to mb omega squared L cosine theta. Oops, I dropped it off too soon. Ft cosine theta equals the mass times omega squared L cosine theta. And I now have a cosine theta in both terms, multiplying in both terms, and I can cancel it out. The tension,
So then we're just left with tension is equal to mv omega squared L.
yeah. Now, in terms of trying to find the actual linear speed, not necessarily simpler, but
Just another equation.
depends on what we're trying to find. This is a much simpler equation to deal with than having to deal with the sines and the cosines. So, for example, if you're trying to find m sub b, then, well, actually, it looks likely you're familiar. If you also recall, the other equation we had was from A, that the tension was equal to MAG. So if we plug that in, we get MAG is equal to MBG, no, it's MB omega squared L. So if I time this thing, if I let's do a crude estimate here. All right, let me get this thing going. All right, so the tube is right at the bottom end of the black ink mark on the string here. Stop that thing. There we go. All right, if someone get their stopwatch going, or just wait for it, we're gonna time how long it takes to go 10 rotations. All right, do I, couple of you ready? All right, so
Just say go.
on your mark, get set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
6.57.
6.57.
What's your, who's it thinking?
Yeah, I got something close to that.
So somewhere around 6.57. Anyone else? All right, that was for 10 swings. So the period, divide by 10, so the period, the experimental period is 0.657 seconds. So I know that omega, that's the time it takes to go around once, it's gonna be 2 pi divided by 0.657. So what is our angular, the angular speed?
.95634479561.
Wait, say it again?
Okay. 0.9.
It's gotta be bigger than 1. Two pi divided by 0.657.
Oh, 0.6.
Okay, so you're off by a factor of 10. Okay.
Okay, 9.56344.
Radians per second.
Why would we put 0.6?
Because the 6.57 was for 10 swings. I wanted the time for just 1. So I divided by 10. L is for is that length right there?
What are you doing in our lab?
Am I? All right, so that is, I'm gonna go with, because the string stretches as I swing it, so 0.7 meters. And that still should not look around. So the mass of A, I'm gonna trust it, although you shouldn't necessarily. So this is 0.2 kilograms times 9.8. You know what? We can do better than that. We know what it is. 9.798 meters per second squared is equal to mass of B times omega, 9.56344 squared times L, which is 0.7. That's meters, this is radians per second. And therefore, the mass of B is
Why don't you put meters per second squared on the omega?
that's a radian. I know. You know, when they install stuff, they don't go, how tall is the instructor?
But there's a square there.
It's radians per second.
Right, there's a square outside the front.
Yeah, it is squared,
Why?
because it's omega squared.
Oh, you.
Thank you. Sometimes. And what do we get for the mass of B?
So.
Please make sense. Please make sense.
So B would have to be smaller?
Yes. You're not getting smaller?
I'm getting like right.
So you'd have 2 times 9.798, 0.2, That's 9.798 divided by 9.56344 squared times
Point 7.
0.7. It's gotta be
Yeah.
less than 1 at least.
I forgot the square.
Ah, that would do it. So what'd you get?
Point 0.03.
0.03 units?
Kilograms.
And I think that is the mass of that stopper. It's somewhere in that range. We're within 30%. Now, obviously, if we just did this one sample, it leaves a lot to be desired in the fact that, you know, how accurate was the timing? It'd be nice if we did several different masses hanging, and then do a plot and then pull off the graph, you know, neat junk like that. So, you're in luck, you'll get to do that.
We'll see how many things will fly.
So you check the string. I talked about the metal shooting flying across the roof, right? Yeah, I did that, okay. Questions?
So the alternate way of solving was using alpha or
Omega.
omega.
Yes. Just use omega squared r. It depends on what you're trying to find. If I'm trying to find speed, v squared over r makes sense.
Okay.
If I'm trying to find mass or something else, the advantage of this is that the cosine
Something
thetas
other
will go away.
than speed, you would use that.
Probably for this type problem. You know, sometimes you go down the wrong path and go, huh, I wonder if I'd used the other one, would it have been easier? And sometimes there's just blind faith in physics that, all right, I gotta be doing, I hope I'm doing it right because otherwise I just wasted an hour of time. And you just plow through and hopefully you get something that makes sense. All right, at this point, I'm going to stop the recording and hand stuff back.